In this precalculus algebra, we're going to talk about what's called the inverse function property. This is also called the cancellation property. You'll see this in different textbooks with different names. So let's start off our discussion by first letting, this says let, L-E-T, it's my handwriting. So we're going to let two functions, f and f inverse, be inverses defined. So let's say that you've got two functions that are inverses, and they're defined on all real numbers. Okay? And let's say that you have the following situation. Let's say that the function f takes 2 and maps out 5. And what would that imply? Well, if the function takes 2 to 5 and these functions are inverses, then the inverse has got to take 5 to what? Well, the inverse undoes what the function does, right? So if the function takes 2 to 5, the inverse has to take 5 back to 2, right? Now, notice that we have 5 inside the parentheses here, right? But this statement above it, this equation above it, says that 5 is equal to f of 2. So I'm going to replace the 5 inside these parentheses with f of 2, because that's what it's equal to according to this top line. So I keep f inverse of f of 2, right? Do you see that the 5, I simply took the 5 and I replaced it. And I replace that whole 5 with f of 2 from the previous line. And then I still have the right-hand side, which is equal to 2. So notice what happened here. This says that if you take 2 and plug it into f, and then you take the output of that and plug it into the inverse, you're back to 2. Let's think of that same situation, or a similar situation happening with the inverse. So if you take the inverse function, and into that you plug, for example, 3, let's say that you happen to get 7 out. I'm just making up these values. What would that imply about the function? Well, if the inverse takes 3 to 7, the function would take 7 to 3, right? Because once again, the function and its inverse, they undo each other. Now, I can also take the 7 here, and I can replace it just like before. So if I replace 7 from above, right, 7 is equal to all of this. So I'm going to replace 7 with all of that. So I have f of what? Well, the whole 7 gets replaced with this whole expression, and I have f inverse of 3. Okay, and that's equal to what? Well, according to this, it's equal to 3. And the same thing happened, right? The same as before. In this case, you plug 3 into the inverse, and then you take the output of that and plug it into the function, and you're back to 3. Now, what I want you to notice about both these situations is that the function and the inverse cancel each other. That is, if you first have the function and then you follow that with the inverse, you're back to where you started, too. Or if you first have the inverse function, and then you follow that with the function, you're back to where you started. Okay? And so we're going to write that in the following way. For all x, this is true. That the inverse, if you take the inverse, let's try that again. So f inverse of f of x, what does that do? Well, you're following the function with the inverse, and that means you're back to x. Okay, that's the situation here. And the same thing is true going the other way. That if you take f of f inverse of x, well, in this case, you start with f inverse and then you follow that with f, you're back to x as well. Okay, so this property is called the inverse function property. Let's box that. This is really important. So this is called the inverse function property. And it's also called, in other textbooks, you'll see it called the cancellation property. Do you see why it's called the cancellation property? Because the functions cancel out, and you're back to where you started inside the parentheses, right? If you plug in x, you follow that with the function and then its inverse, you're back to where you started. And the same thing if you reverse that order. Now you should note that these are also, this is composition, right? Where you take the output of one function and use that as the input for another. So this is f inverse composed with f, and this is, the other one over here is f composed with f inverse. And it says if you do that, you end up getting back to, you're back to where you started. Now it turns out that you can also show that if you can verify these two properties, that implies that the two functions have to be inverses. So that's what we're going to do in these next two examples, is we're going to take two functions, find their composition, and show that you're back to where you started, and that'll imply that the two functions are inverses. That is, let me say that once again. We're going to start with two functions, take their compositions in both directions and show that you get x out, and then that'll imply that the two functions are indeed inverses. Okay, let's see an example of this. Show that f and g are inverses. Okay, so what we do is we first take f composed with g, and then we're going to take g composed with f, and we're hoping to get x after both of those. So first we'll take f composed with g, and remember from our video on compositions, this is f of g of x. Okay, and what does that say to do? Well, that says take g of x, right, and use it as the input for f. So this is going to be f of, okay, you replace that with g of x, and g of x is all of this. So it's f of 4 minus x divided by 3, and then you use that as the input for f, which is right there. So it's going to be 4, take away 3. Okay, replace this x with all of that. So it's going to be 4 minus x divided by 3. And then what happens? Well, the 3's cancel, and then you distribute the negative, so you get 4, let's see, minus 4 minus x, and that's equal to 4 minus 4 plus x, and notice that's equal to x. And that's what we wanted it to be equal to, right? So what we're basically saying is that you're back to where you started. If you first put x into g, and then you put that into f, you're back to where you started. Now, in order for these to be inverses, you have to verify it going the other direction as well. That is, you have to verify that g composed of f, that's also equal to x. So this by definition is g of f of x. And once again, what we do is we replace f of x with what it's equal to, which is 4 minus 3x. So this is g of 4 take away 3x. And what this implies is that you replace x and g with 4 minus 3x. Well, here's g, so we're going to replace the x with 4 take away 3x. So we're going to have 4 take away 4 minus 3x, right? All divided by 3. And what do we get? Well, that's going to be, in the numerator, 4 take away 4 plus 3x, and then divided by 3. And these cancel out, and you get 3x divided by 3, which is equal to x. And that's what we wanted, right? So that we showed it's true in both directions, and that implies the functions f and g are indeed inverses of each other. They undo each other. So these two functions, f and g, are inverses. By the way, the inverse of a function is unique. There's only one function that's the inverse of a given function if the original function had an inverse. So in other words, f's only inverse is g, and likewise g's only inverse is f. Okay, let's see another example like this. Let's show that f and g are inverses for these more complicated functions. So once again, we'll take first f composed with g, and we get, let's see, that's by definition f of g of x, and we're going to replace g of x with all of this. So we have f of 1 over x, take away 1, and then we're going to replace x in f with all of that. Well, here's x in f, right? So that x is going to be replaced with all of this. So it's 1 over, okay, the x gets replaced with 1 over x, take away 1, and don't forget you still have the plus 1 there, and then we'll simplify that. So the negative 1 and the positive 1 cancel, and you have 1 divided by 1 over x is still in the denominator, and that's the same as 1 divided by 1 over x, and that's equal to 1 times the reciprocal, which is just x, and you just get x. That's the first part that we wanted to verify. Second part is we want to look at g composed of f of x. And that by definition is g of f of x. So we replace f with what it is, which is 1 over x plus 1. So it's g of 1 over x plus 1. And let's see, now you take all of that and plug it into x for g, which is right there. So it's going to be 1 over, okay, this x gets replaced, right, with all of that. So 1 over x plus 1, and then don't forget you still have take away 1. And this, just like before, right, it's 1, let's do it over here. You have 1 divided by 1 over x plus 1, but that's the same thing as 1 times the reciprocal of this, right? And that's just x plus 1. So this whole thing right here is just x plus 1, and then you take away 1, and that's equal to just x, and that's what we wanted to show. So take these two results together, and that implies that f and g are inverses. Okay, so we're also going to see the cancellation property arise later on when we work with the exponential and logarithmic functions, so this is something we want to keep in mind. Okay, until next time.